Yeah, thanks for having me here. Hopefully I give you the overview you're looking for of everything. So this presentation's a little bit about this open source hardware project I've been working on. It's almost the total opposite of his project because rather than securing us, it's trying to break security of devices. So, you need both. This is what you'll see. So hopefully you're not sick of hardware and math because this is also in my presentation too. So I'm from Halifax, Nova Scotia, Canada, and I'm almost done a PhD at Dalhousie University there. As part of that, I developed this open source hardware and have been spinning up a company basically trying to sell the hardware. If anyone sort of has done the PhD and then started doing something else, this last step takes a while because you get so distracted. So that's really, what are we doing here? I want to show you fundamentally a type of physical attack you can use on hardware. And when I say hardware, I'm really thinking of stuff like embedded devices, chip and pin credit cards, little Internet of Things devices, but it's also applicable to mobile phones, hardware security modules, all sorts of hardware, even up to PCs. Some people have applied these attacks. These attacks have been known for a long time, but I'm showing you how to do them with open source hardware and software, as well as fully documented. So this is sort of the real difference from previous presentations you might have seen, is that a lot of these techniques and tools you can just download and use. You might already have an oscilloscope you can use with them, or you might need some low-cost hardware or build your own hardware. So the open source tools on chipwhisperer.com, if you're interested, all the Git repos and everything are there. The website of the company is newae.com, so that has some other details of the tools. And I also have a website at oflin.com, which has my blog on various things I've done with the project and related topics. So all these links will be at the end, and these slides are posted online as well. So you can get all the links in here. So I'm going to give you the one sort of caveat to this presentation I always give, is that everyone wants the sausage. Everyone wants the awesome attack that you put your hardware on the table and you plug it into the magic device and it just works. It's impossible for the attacks I'm talking about. Fundamentally, you have to understand how it works, how both the hardware device you're attacking is made, what the underlying algorithm it's using, some details of how it's implemented even. And you have to use that and then apply these attacks. So you need to know how it's made before you can get to this stage. So that's the other caveat I give you. And as part of that, I'm going to be giving you, some really quick overview of the math involved in these attacks. But I'll show you a few real live attacks as well to show it's not, as difficult as you might think at first. So as I mentioned, I'm doing a PhD. That's my blog there, oflin.com. I previously worked at Atmel as a sort of embedded engineer, doing a lot of Internet of Things type protocols. So obviously I hate Internet of Things devices now, having spent so long developing them. I've also done a lot of security talks since then. I moved into embedded security, so I've been to DEF CON and Black Hat and stuff like that. And more recently, done this open source project, Chip Whisperer, that I'm here to talk to you about a bit. Chip Whisperer itself, we recently did a Kickstarter. So if you're interested in Kickstarters, you can talk to me about that. And there's about 300-ish people or so, 331 backers. Around 300 got a little bored. And the objective is to teach you about side channel power analysis. And this will be a little overview of that. So the most basic side channel you might be familiar with is the timing attack. So the timing attack says, say we have some crappy C code that's designed to check a pin has been entered. So it's not totally brain dead. We read the pin from the button, so it waits for the user to enter all 6 characters in this case. And once it reads 6 characters, it's going to check, is this pin the correct pin? And the easiest way to do that is you have a little loop, and as soon as it's wrong, we break out of the loop and we return. So this right away opens up this timing attack, because if the first digit is wrong, so if the correct pin here is 1, 2, 3, 4, 5, 6, if the user puts in 0000, it's going to see, oh, the first digit's wrong, I return. So based on how long it takes, whereas if the first digit's right, it'll go through the loop once, and then if the second digit's wrong, it breaks then. So based on how long that loop takes to exit, which might be that it puts an LED high and says that's wrong, you can learn something about what digit of the pin is wrong. And this isn't, like people put up these slides and you go, well, no one really does that, surely. So as an example, this was sort of a crappy password-protected hard drive. It never claimed to encrypt the data as a note. All it did was mangle the partition table. When you put in the right pin, it unmangled the partition table so Windows could see it. So it never claimed to have encryption, but it did say, if you don't put in the pin, it's useless. And they did that mangling so that if you remove the drive from this enclosure and just plugged it into your computer, it also wouldn't appear. So it wasn't completely terrible. But it had this type of really basic timing attack. So to give you an idea, I opened up the cover of the drive, and there's oscilloscope probes on two things. One of them is on a button, so you can sort of see here there's a button. One is on a pin of a chip, and this pin goes to the LED that it turns on when you put in the wrong pin. There's always a little bit of extra work involved to apply it in real life. In this case, you need to figure out that the microcontroller isn't always waiting for you to press a button. Our meat hands are very slow for the microcontroller, so it just wakes up every 100 milliseconds and says, hey, did you press a button? Okay, I'm going back to sleep. So you end up having to check one of these lines because it'll put the line high when it goes to read the button. And you can then get the time from when it reads the button to when that error LED comes on. So let's look at that. So in these slides, the blue line here, this is the button. So this weird pattern is it doing this scan. And the red line goes low, when the error LED goes on. And you can see there's this difference in time. So the right password is 123456. So if I put in 06666, we see this certain time delay, between from 0 going high, or from the scan of the buttons and from the error LED. If I put in 1666, you see, hey, that's a little longer. And that's because it's now gone through the loop an extra time before the error LED went on. And if I go 123, so the first 3 digits are correct, we see, so you might not be able to read, but it's printing the delta time up here. So this is like 60 microseconds, and then 64 microseconds, and then 80 or 79 microseconds. So you can see it is, taking a little longer to go through this loop. And it's just one of these chips here, I think is an 8051 core somewhere that's running the actual algorithm. I forget which one. Pretty sure that guy. So that's a basic timing attack. And what people might do is they'll say, okay, well, that's easy to fix. All I'm going to do is do a random delay, after I fail, so that they can get no timing information. Or they might say, I'm not going to give any response when wrong. So if you put in the wrong password, the drive just locks. It never has an output, so this error pin is never going to change state because it doesn't tell you when you errored, it only tells you when you're correct. The problem is we can still see what the device is doing when we look at the power usage of the device. So this is another, I don't have it here, but this was a bootloader where it had a password protection on it. If you sent the wrong password, it simply never responded. It just spun into a loop and you had to power cycle the device. The problem was, because it was a very small bootloader, tried to make it as small as possible, it would, as soon as it detected the wrong digit in a password, it spun into that infinite loop. And what you can see here is this, in blue, is the power usage of the device. So power usage. And when it's actively receiving the password, it's taking more power. So this is, because of the measurement, it's inverted. So more power is this way. So that's more. And less is up. And you see that, it's doing processing of the data. As soon as it stops listening, the power usage changes substantially. And so you can know that right away, hey, that byte was the wrong one. So we just have to enumerate, for each byte what the possibilities are. So we've greatly reduced our key search space. Now these types of attacks, so there's an example where, the first byte's wrong. So you see right away, it stops receiving it. So for all of these attacks and what I'll be talking about, we need ways to measure the power. Very briefly, we have, a microcontroller. So if we were doing it against this device, there's various chips that are using power. And what we want to do is we want to insert a resistor into the power line. So this would be, the VCC pin for the chip. So this is your microcontroller, MCU. And we're just measuring the voltage across that resistor, really with an oscilloscope, not with a DMM. And this is how we get our nice power usage waveforms. And if you have a real board you're attacking, that can actually be not too difficult. So this is a view of what's called a TQFP package. This is sort of a top view, so you can see these are the individual pins here. And all I've done is one has been lifted up and a very small resistor inserted into it. And over here, there's a wire going off. And it otherwise goes to the rest of the power plane. So this is exactly like the, so that's the resistor there. This is exactly like this diagram I just showed. We're able to achieve this power measurement on a real board, with a fairly simple modification. The other thing we can do is we don't even have to physically modify things. We can use what's known as a H-field probe. Basically, a changing current generates a changing magnetic field. We have simple probes that look like this, so you can build something like this for a few dollars, or buy one for 50 to $1,000 if you want a really high-end probe. But this probe can sense that changing magnetic field. The field lines through it. It generates a very small voltage, which you can detect. This changing magnetic field is related to the current, and therefore we can do this exact same analysis, as we were doing with the resistor, without modifying it. It also means you can attack if you have a BGA device, so the ball grid array, where you can't lift the pins. You can't do this pin lift thing, wherever that photo disappeared from my slides for some reason. You could use the H-field probe. So that's how we measure the power. And that's just, real simple power analysis to detect what the device is doing, which is cool, but not the limit of what we can learn. What's really interesting is that we can directly break cryptographic keys out of hardware devices. And this is something called differential power analysis, which is an even more powerful tool. How this works is that on a digital device, internally, it has these lines that it's switching. So there's these bus lines that run all over the chip. And the microcontroller can switch these lines either high or low. So if it changes it to a 1, it connects the, what I call the VCC here, the positive supply, to that rail. If it changes it to a 0, it conducts the ground or the 0-volt supply to that rail. Now that rail, is literally a piece of wire inside the chip. It has some capacitance. So really what we're doing is we're changing the voltage on this capacitor here. And it might be 3.3 volts, say it's a 3.3 volt part, and then it might have to change it to 0 volts. If you remember sort of high school physics, changing the voltage on a capacitor physically means we're moving a charge, physically means we're taking power. So if you were to look at a digital device and say, what happens when two of the data lines, so typically the data buses might have 8 bits, 16 bits, 32 bits, 64 bits, however big the standard integer is normally. What if we look at the power consumption as it puts a word with 2 ones on the data bus? So if 2 of those data lines are switching to high, we actually see a larger spike than if just one of those data lines is switching to high. Or if neither of the data lines are switching to high. So if they're switching low, we won't see this positive spike at all looking on one of the power rails. So what this would suggest is that the power consumption at a very, very, very fine level is actually directly related to how many ones are going on the data bus, which seems crazy because we're learning quite a bit of information about the chip. And this is actually completely the case. So this was some measurements I did, and Hamming weight is the number of ones going on the data bus. And this is a measurement of the power related to the power. And you can see it's almost a perfectly linear fit. There's some crazy kink at the end here, possibly due to scaling issues, but you do see it works very nicely. So you really can learn this information about what's going on inside the chip with just power measurements. Okay, so at this point, it still may not seem like it's that interesting because all we're learning is, how many ones are on the data bus of this chip here. So let me break some crypto for you with that simple information. I have a system under attack here. This is, your chip. I have a scope to measure the power, so this is your resistor for the power measurement here. And inside that device, let's say I know it XORs some input data with some unknown secret key here. So we have this secret key. It's XORing that input data with the secret key. And critically, I don't have access to this output here. Where it goes inside the chip or, something crazy like that. I don't know. But I'd still like to recover the secret key, which would seem impossible. But using this power measurement, we can do that. Because you can consider that, well, what if, let's say I put in 88 hex. I know it XORs it with the secret key, in this case EF. It's going to generate hex 67. Hex 67 has 5 bits set to 1, so if you convert that to binary, count the number of ones. And same thing with every other input we get. We could figure out what the Hamming weight should be over the data bus. Now, eliminate what we don't know. We don't know the secret key. This here we don't know, and we don't know what that output is. But we do know, or what I'm claiming we do know, is the Hamming weight of that output data, or of that data in the chip. So we actually know what the result should be, just the Hamming weight. So the final step is we just do a real simple guess and check. We can check every possibility for that secret key. So here I've set it to 00, and I said, okay, I put in hex 88, let's XOR it with 00 and see if what we expect to measure, this hypothetical measurement of the number of ones, matches what we actually measured on the physical device where we don't know any of that. And all we do is we then try, we say, okay, that didn't work because, I measured 24344 and I expected to measure 55635. So it's wrong. If it's 01, it doesn't match up again. Eventually we'll get to the point where we say, well, if I guess the secret key, or the byte of the secret key was EF, what I would expect that intermediate value to be, meaning what I would expect it to leak, actually measures our leakage. So we have a model of what we expect it to leak, and we have measurements, and we simply match them up. So this is the basics of differential power analysis. What makes this cool is that when we look at a lot of algorithms, so this is AES 128, how it operates is that, it has 128 bits, so it has these 16 bytes inputs, these 16 byte keys, but right at the input, it actually just operates on 1 byte of the key, 1 byte of the plaintext. It XORs them together, and it actually passes them through a lookup table. What this means is that with this differential power analysis, we no longer care that it's 128 bits, or if it's AES 256. It doesn't matter, because we're breaking it 8 bits at a time. And that guess and check, it's only 256 guesses, and it just scales linearly with however many bytes we have. We no longer have this crazy growth in the search space. So you can break it, and I'll show you on a laptop in sort of a few seconds type thing. The only real thing you have to remember is, so when we were doing these measurements, the crypto device is running with the secret key. So this is the real important thing to remember. Side channel analysis needs, the crypto device running with the secret key you care about. You may not need to control the ciphertext or the plaintext. You don't necessarily need to control them. You do need to be able to either deduce one or two of them, so either the plaintext or the ciphertext, or possibly a part of it. If you know part of it's fixed and part of it's not, that's enough. So counter modes and stuff you can still attack. It's a tiny bit more complicated, but very doable. But the critical part is that the secret key has to be in the device running. Why I say that is that, if you have a hard drive on a table that's been encrypted, side channel analysis is no good for you. It's not actively doing anything, encrypting or decrypting the data. If it's just sitting there, the key's not loaded in the engine, so you can't use it. If it was, actively being in use by the user, you then could use side channel analysis on the device. Despite that, there have been a lot of devices that have been broken. So this was various papers. Some of them you may have heard of, some of them not. So a number of them, for example, FPGAs that have protection in them against loading, stealing the design, or loading unsigned files. You can break them. Some crypto engines, so this XMega, for example, is just a peripheral in a microcontroller, is breakable. These devices, where these HSC devices are in key fobs, so I know older, maybe newer Volvos use them too, but they use a broken, basically algorithm and implementation of the algorithm in the chip that you can break. So there's a whole bunch of stuff that it has been applied to. Just because you have hardware crypto, is the point, doesn't mean it's secure against this. So Google Vault recently had their own sort of hardware security module thing. I never fully saw the details if they were all released. But as part of that, they had an AES FPGA AES core, and they had some notes in there that their design avoids differential power analysis attacks because they use some other design. This was entirely false. You can perform a differential power analysis attack on their implementation just as easily as not. So a lot of the reason this happens is people don't have the experience of doing the attacks themselves. They don't have the resources. So part of starting this whole project is to give any engineer doing any sort of crypto tools the ability to do differential power analysis attacks, test hardware, validate vendor claims. And that's really the point of this whole project. All right, so that's the math introduction. Let me show you a basic power analysis attack. So what I have is, I have this board. This was the one we did the Kickstarter for. So it does a combination of the, let me just get a shot of it up here for you. Oops. So this is the board, and basically what you have is there's half of the board is programmed with an algorithm of interest. So in this case, I'm just doing, sort of research type work I'm showing you. I'm not attacking a commercially available device. I've taken this device and I've programmed it with an open source AES implementation. This one is AVR CryptoLib, is what I'm using, but there's a few other implementations you can test. This half of the board, so that's half the board. The other half of the board here actually does the physical power measurement, so it has an ADC and amplifier and stuff like that to perform this power measurement, and then downloads it to the computer via a USB microcontroller and FPGA. So let me just get back there. Okay. So what you're seeing here is that'll stay hopefully. What you're seeing here is that waveform is the power consumption of the device as it's doing AES encryption. So you can view, for example, the input and output, verifying that it's actually performing the correct encryption. So it's just encrypting 16 bytes just as a simple test. You can see, for example, if I tell it to encrypt the same data over and over, you'll notice this power consumption curve isn't jumping around quite as much as if I go back to telling it to encrypt random data. What you'll see is that you can see sort of the spikes moving up and down. So it's just showing some data dependency within the traces. So to actually do an attack, what I need to do is tell it to encrypt a bunch of traces, a bunch of data, and save those traces. So I'm just going to call it test live sect. So I'm just recording the data. So it only takes a few seconds. It just sends it a bunch of data, says encrypt this, encrypt this, encrypt this, and saves the power consumption traces. The other half of this, so all of this, by the way, is open source, written in Python. The only caveat I give you is that I started this project about 3 years ago. 3.5 years ago, I had never used Python. So if you look back to some of the original code, the quality sort of improves over time as I learn how to program in Python. So a lot of it's been fixed since then, but not all of it. All right, so this is the capture. So this is sort of the waveforms I just captured. And it's just going to do this guess and check with increasing amounts of traces. So I'm going to make it run. By default, it runs too fast to actually make a good demo. So what's happening here is in red, the correct key byte, I've told it what the correct key byte is, will filter to the top. It's ranking what the most likely key is based on how many traces it's using. So you'll see, normally it's around 50. It depends how noisy everything is. So it's about 40 traces. So all in red, you see the correct key is now at the top. So it's completely recovered, AES 128 key in a real open source implementation of the AES encryption algorithm. And it doesn't take very long at all. So the other question people have is, like how did I know when to look for the power? Because it's doing a whole lot of stuff. The cool thing is that everything that's not the encryption sort of filters away in the algorithm. So what I've done here is this is actually showing you several points in time, so it's 3,000 samples. In real life, what you would do is you send it, the command to say encrypt. In reality, you might send it an authentication command, and you just start recording power until it returns the result. When I run the algorithm, you see this big spike, and this is for recovering byte number 3 of AES. If I say, okay, where did you recover byte 4, you'll notice this other red spike at the next point in time. And in this case, there's just a for loop in AES, doing each of those XORs and SBox lookups. And you can see that it's simply, you can see the offset of how long it's taking to run through that loop. So you don't really need to know exactly where the AES itself is happening. The algorithm will pull that information out for you. And as it goes on, comes a little slower in redrawing. But you see the same, marching on in time. And that's just the for loop inside the C code as it's running. So that's a really basic AES attack. So in that case, I have a device programmed that just does AES and returns the results. How do you apply this to real life? So a few other examples I've sort of documented. AES 256 bootloader. So in this case, it's AES 256 instead of 128. It's based heavily on a number of microcontroller manufacturers make these app notes that say, hey, do you want a bootloader? Great. You can now have a bootloader that only accepts, assigned code. And you can post the firmware files, but no one can use it because it needs the key inside your device. The problem with this is that when I send it a firmware file, it's going to decrypt it. It's going to throw it away once it realizes it's fake, but it's going to do this AES decryption. And this is all we need for a side channel attack. So if I'm able to send it a bogus firmware file, I know what data I've sent it, I know when it does the decryption, roughly, and I can force it to do a whole bunch of them. I just reset the device and send it a new file. So in this case, the format, so the online published one, I've basically collected a bunch of app notes and rewritten a generic bootloader, but it uses all the same principles. Most of them designed to run on small devices. What you have is you take here's, the hex unencrypted file or whatever, a binary. So that's the file they want to distribute. They chop it up into, they're using 12-byte lengths. And they just add 4 fixed bytes at the beginning, so this gives you your 16-byte block. The idea of these 4 fixed bytes is that's going to be their signature. Every block they decrypt, they're going to check. Do those 4 bytes match what I expect? If not, stop. Don't load it, throw it away. They then use AES 256 in CBC mode, so there's an initialization vector, which is also programmed into the device, so we'll need to break that as well. They then add, a header and CRC and everything else you expect. So it's a really basic serial communications protocol for downloading an updated firmware. So to break this, you would physically need the device because that's the device with the encryption key in it. And all I would do is I would just send it a bunch of random binaries. And in fact, all I'm going to use is you could synchronize in a large file how many decryptions it does. In my case, I just send it the first block till it decrypts and then resets it. Our objective is 2 things. We want to recover the decryption of the key used in the AES 256 decryption, and we want to recover the initialization vector used as part of CBC mode. As a note, you don't fully need that because if you don't recover this, so if you're unable to recover the initialization vector, which is actually slightly harder, you would still have the contents of the entirety of the file except those first 16 bytes. So if you just wanted to reverse engineer it, that's probably fine. Normally that first 16 bytes is just like a jump table or something like that. It's not too difficult to figure out, what it should be. So in that case, you don't necessarily care. It may be too, if you know what those first 16 bytes would be, because you know the architecture, it has a very standard sort of beginning part of the file. If it's just the jump table and it's using some standard addresses, you can actually break the IV by sort of reversing it. Once you know the AES-256 key, if you knew those first plain text, you could figure out the initialization vector. The only difference with AES-256 in this case is that it does it in two 16-byte chunks. So the first bit of the decryption is almost the same as what I showed you before. We have the secret key, we have the input, the ciphertext in this case, and we're looking at the output of this inverse SBox lookup table again. And we can recover that. And once we recover that key, so we have to do that attack first, we can then attack the next round because it uses the next 16 bytes of the key are used in that output. Oops. And then it just continues on. So once we have those first 2 bytes, or the first 2 16-byte blocks, we can run the AES key algorithm backwards to get the complete initial key. So those are the 2 things we need to attack right now. There's a tiny bit of complexity when you physically do it. In this case, the AES implementation, so I'm using one from the app note. It works fine for that first 16 bytes, so they're very nicely synchronized. So this is like, 20 decryptions. So I've sent it 20, I don't think I spelled that right, but you get the idea. 20 blocks, and I'm viewing the power consumption. What you see is that it looks very nice and aligned. At some point, it looks really messy. So they're no longer lining up. All that happens is stuff becomes desynchronized. There's some, random delay when it's going through the loop. In this case, they have a timing attack in their AES, but it could be you have an interrupt. If it's running with an OS, it may have an interrupt partway through the encryption, so you've got to resynchronize stuff. That's very easy to do in the software. It just shifts it all based on a pattern. This type of stuff is well known in image processing and video processing. It's not remotely new or difficult. What you get is the same sort of device, a small microcontroller, in about 60 to 80 traces, somewhere around here, with almost 100% of the time. So the success rate is saying how often did I recover the entire key. Almost 100% of the time, in about 60 decryption operations, I can recover those first 16 bytes. It takes a little longer to recover the next 16 bytes, and in this case, up to about 120, it is almost always recovering the full AES-256 key. So it doesn't take a lot of operations, like 120 decryptions. You can do that in 5 minutes, even if you have to reset the device in between every attempt. So that's one example. Another example is something like an 802.15.4 node. So this is 802.15.4, if you don't know. You might know it by the name Zigbee, or Zigbee IP. There's a bunch of different versions of it. But it's just a sort of low-layer protocol for low-power radio devices. It's actually used by a lot of other protocols as sort of an underlying layer, including Thread, I believe, is the Nest. So the Nest thermometer uses 15.4 for some of its local communications. What's really interesting about this is that a lot of 15.4 nodes will thus have something else on them. So they might have Wi-Fi, or they might have Ethernet. A lot of the time, they connect into a larger network. So if we can get an attack on the 15.4 side, we may actually be able to, fuzz that interface to find bugs, to hop over to another interface. And that's what sort of makes it really interesting. It's not just the case of, hey, you attacked 802.15.4, okay, you can turn off my lights or something dumb. You might be able to get further on to the network using this as a base. And the sort of threat model we're using is that we assume these 802.15.4 nodes, again, are normally cheap and crappy, like light switches, lights, little thermometers. it might be pretty easy to actually capture one of these. So the research I did was this is a 802.15.4 development board. So it's loaded with a legitimate 802.15.4 stack that respects all the standards. And one of the fun things about these stacks is, as you would expect, if I send it an encrypted frame, all it's going to do, it does some validations, does this frame look valid, blah, blah, blah. And at some point, it decrypts the entire frame, which is what you expect it to do. If the message authentication code fails when it tries to validate it, it's just going to throw it away, as you expect it to do, and it won't tell anyone about that. It's just a low-level thing. It assumes it's noise or someone misconfigured something. But what this means to us is we actually now have this attack ability, because we can force it to do decryptions when we want it to. The question is, do we control the input? And more or less we do. It doesn't. It's used in counter mode, so you only control little bits of it. There's an AES counter, which is always set to 0 at the start of a frame, so for us it's always 0. All we control really is there's 4 bytes of frame counter. The address stuff, you have to use a legitimate address because it validates that address as one it's talked to. You can spoof it, that's super easy, but it has to be one of a known address. We have about 4 bytes of what it calls the frame counter, so we control these 4 bytes of the AES input. Everything else is more or less a fixed value. The hardware itself, so this node internally has a hardware AES accelerator, so it's not doing the software version I was just showing you. It actually has a peripheral in the micro that's decrypting it. As it turns out, this hardware AES engine is vulnerable to the side channel power analysis attack, which is mostly the case for any device that's not designed to be resistant to it. So your credit card is designed to be resistant. An off-the-shelf microcontroller is not. And what this shows you is that, by the way, the scale on this one is the inverse. It's called the partial guessing entropy, so the entropy in the key. How many guesses do I have left in the key before I recover the correct one? If it goes to 0, no more guessing is needed. There's no entropy in my guessed key, so it's more or less recovered. What you end up with is somewhere around 6,000 to 10,000. It either recovers the key or it's so easy to guess it because there's like 100 guesses left, it's effectively recovered it. And so what's interesting here is that, if I send it 10,000 messages, we're able to break this encryption algorithm. And it's not that hard to send it 10,000 messages. It's just a wireless device, and get it to decrypt them. The other cool thing is that I've never broken this device. I've never, opened it up. I've never reflashed it. It's still going to be on the network if it's in radio range. It's still responding to all the normal messages. So it would be also hard to detect this type of attack. Eventually, once you get the key, at this point, you'd be able to send messages back to this guy, the 802.15.4 coordinator, and whether that's that you want to, pretend you're the outside node, or more likely, you want to use that to, exploit further up the chain. So that's another reason you might want to care about side channel power analysis. Now there's so that was breaking the crypto. There's a whole other field that's interesting called glitching. And this is almost sort of a more, I don't want to say basic, but more fundamental way around some of these security measures. And what this is, if you have some sort of authentication module, there's always somewhere that it has a check. So in this case, this is in Linux, the PAM authorization. So it says, if the user ID is not equal to 0, do these checks. Otherwise, return true. So if you could cause it to execute this check incorrectly, you wouldn't even have to break any of the password store or the crypto on the device. You might just be able to get the authorization you need right away. Same thing with Android, so verify password and unlock. At some point, it has a check that says, check password. If that password is good, it says, okay, we're fine. Otherwise, it goes through its failed attempt. So regardless of whether, go back here. Regardless of whether or not that actually happened, we can, what our objective is to simply screw up the system in a predictable manner such that it thinks the password passed the check. We don't know what the password is, but we just make it pretend it passed. So I can show you 2 quick demos of this. You can do this on little 8-bit microcontrollers again, just like the one I have here. And this hardware, by the way, is able to do some of the power glitching and clock glitching I'm going to be showing you. But I want to show it to you on something more interesting than just that little microcontroller. So I have 2 videos of running it on a Raspberry Pi and an Android phone. So the demo code I'm running to make it easier to see for the demo purposes is I just have this for loop. So there's an inner loop and an outer loop. And the objective is simply to cause it to either break out of this loop or otherwise do this count incorrectly. What this means is that it's either skipped over an instruction or executed it incorrectly. In practice, what this means is that if you're able to get that to work, it's more or less a matter of either timing or luck to try to get it to break over specific instructions within the device. So for the Raspberry Pi, how I'm going to do this is I'm actually going to short the power supply of the Raspberry Pi in a very, very predictable manner. So on the Raspberry Pi, it has this core voltages here, VDD core, and all I do is I have a wire attached to that section of the board, so the core voltages, and the other side of it, so there's like the side of the capacitor, this little tiny wire soldered on. On the other side of it, I have it connected to an electronic switch. So this is like a MOSFET that's $1 off DigiKey. So it's all stuff you can experiment with. And all this switch is going to do is when it's enabled, so this is the regular voltage here is, I think you can't quite see, but it's about 1.2 volts, something like that. So when I turn on the switch, it goes down to 0 volts. It's shorting it out. And actually, when I release it, due to how the power distribution in the Raspberry Pi works, you see it actually shoot way up. It goes like way out of range and has this crazy ringing and stuff like that. This is not good for the electronics, and it will cause these glitches to happen. So let me show you a movie of that. So there's no sound in the movie, so you're not missing out on anything, don't worry. Go full screen. Okay, so this is the Raspberry Pi, the same thing I'm showing you. And I'm going to compile that really simple loop on top of Linux. So I'm not running this, right on the hardware. On the side there of the screen, I have the device pinging just to confirm that it's operating the whole time. And I have that same setup. I showed you the MOSFET, and it's connected to, in this case, I'm using a chip whisperer device to generate that pulse. You can, in fact, use a pulse generator or program Arduino to set an I/O pin low and high for a certain amount of time. It's all about generating just that controlled, short on the power rail. And again, this is the C code I'm using. So let's run it. So you can see it's giving us the count in the inner loop, the count in the outer loop, and the 2 multiplied together, which is just the total number of counts it's gone through. So if something screws up, those counts should become incorrect because it's going to skip over one of the loops. It'll think it executed it, but it actually didn't. So you'll see the total count will be wrong because it didn't run through all of the loops the number of times it thinks it did. So all I'm doing is I'm inserting those glitches. You can see live the power change there. And if we look back at the window here, if they don't scroll out, we can see at the top here, there's like this 2,004,995 or 000. I was off by 1 when I started that number, I'm sorry. But you can see it's incorrectly done the count. And if we have both of them here, I can try that again, and you'll see it incorrectly do the count. And you notice it didn't crash. So it's still pinging wherever the ping went there, but it's still running the Linux system. It's only glitched that user land application. So that's what's sort of interesting, is that it's not like we have to be very concerned that it's only running one thing. you can in fact cause glitches in applications running on generic hardware. And the same thing for a Android phone. I'll show you. Oh, I don't have any photos with that. Let's see. Okay, so this is a really old Android phone that I didn't want to break my actual phone. So I've done more or less the same thing. I have a photo will come up here in a second, but there's a very fine wire that's going to one of the core voltages on the main sock there. And that sock has a whole bunch of stuff in it, so you can see kind of that wire. And that wire goes to my electronic switch to short the power supplies of it. And we're sort of doing the same thing. So I'm going to have a very zoom in here. I have that little double for loop. And when I hit start, it just does a bunch of calculations and the results on the screen. So I never wrote an Android application before. This was the first one I've done. So you'll see it's got issues, but you see the same thing, 5,000, 5,000, 25 million. So it's just doing these two loops and checking, hey, did I go through all the loops or did I screw up? If I screwed up, it means that I jumped over an instruction or I thought I went through something I didn't. But if I insert glitches while doing it, we can cause some incorrect results to happen. So I think the next time I do a glitch. On the Android, as you'll see, sometimes it doesn't work as you expect. So I have the same setup here. It generates a glitch. In this case, it actually just crashed the application. So it's not 100% reliable, but it will work sometimes. And you'll see it's still running. All the background tasks are obviously still running. So there you can see one of the iterations through the loop. It gave the totally wrong number, so it seems like it either reset a value and ran through it a bunch more times or something like that. So it's interesting because it's very easy to do. It doesn't, I haven't done any really invasive modifications to the hardware here. I've simply soldered on some wires. And this time, so there you see another glitch inserted there. And you can just keep going. So that's sort of a real quick introduction to glitching. And you can do that on, so for my demos, I've done this on, the XMeg on this. I've done it on other small microcontrollers, ARM microcontrollers, Cortex M4 and M0. So it's a very generic type of attack you can do, causing these incorrect calculations. Well, here, I talked about using it to bypass passwords. You actually can use this to break crypto as well, because you can do stuff like, AES should be running through 10 rounds. If it only runs through 1 or 2, that's not good, because it will now leak key information into the ciphertext. Just as I've broken the for loop here, you can break the for loop within crypto algorithms to cause them to be considerably weaker, because they haven't run through every possible loop. And this is both hardware and software has this type of vulnerabilities. All right, so the final thing people often ask about is, what about triggering? There's a few different ways. So this is, how do I determine when to either glitch or when to trigger, my side channel measurements? The two most basic things I can show you with that is, one is the communications protocol. So here I'm triggering on data sent to the device. So when I send it the authentication request, I can trigger on the bit pattern indicating that message is going over the wire and trigger the capture. The other thing we can do is actually trigger on patterns within the power measurement. So in this case, these lines here is actually part of a for loop while it's copying some pin code to an internal, copying the actual pin code to some internal register. And we can actually see that for loop happening. It goes through, 4 or 5 times. These all make very unique signatures, and you're able to set up triggers to actually look for them in real time in the measurement and trigger on that. So some of the Chip Whisperer FPGA code is able to do that. Not this little version I have with me, but an earlier version we had. Again, everything's open source, so you can mix and match. You don't have to just use, this isn't just a tool to buy, it's something to experiment with, but it's possible to do that. All right, so this is what I was talking about, the original version of the Chip Whisperer. It used a large FPGA board that plugged in. It was kind of expensive because you had these different boards that had to plug together, came from different places. But it was designed, well, let's try to make as simple as we can a lab setup. Again, it's not quite at the level that hobbyists can use it because it costs like $1,500, or if you build it, it's fairly complicated. So the real objective, as I showed earlier, was to do this Kickstarter for a really low-cost, fully open-source, the PCB design, the FPGA, and the firmware and the micro, and the software is all GPL licensed, all freely available. So it's, it's not one of these projects that has a fake no commercial clause or something. It's legitimately, you can do whatever you want with it. The software I've already showed you. The interesting thing with the software, so this was the capture and the analyzer, is that you don't necessarily need to use it with just this hardware. So there's other FPGA boards you can interface to if you want to do the capture. So this is using a ADC board here with a AVNet, oops, that should be ADC, AVNet LX9 board here. And it's connected to, a breadboard where I have the AVR microcontroller set up to do the test algorithms. You could build your own, so this is like a Arduino-esque, target board, and connect it to an oscilloscope. So there's already drivers to use picoscope and one or two other scopes in the software. So that's for doing just the power measurements, not the glitching. And all of this has what I consider fairly good for an open source project, documentation. So there's a wiki page with some of the stuff, and, oops, where is it? As well as some, documentation that goes through the tutorials of, hey, here's how you do an AES attack. Here's how you do the AES-256 bootloader attack. So I really hope that it encourages you to say, hey, this is something I can go through, and I can look at these attacks and start to learn about how to perform them, as well as how to test, my own hardware I might be designing, stuff I'm using from vendors, anything like that. That's the real objective of this. And as a bonus, because it's a hassle to travel with stuff, I have the Chip Whisperer light here, and who's interested in one? We're going to have a throwaway contest here. This section, front? Okay, let's see how we do here. If you get it and you really don't want it, give it to someone with their hand up. I can't go that far back, so I'm going to go like this way somewhere. Okay, we're going to do this empty box style. Okay, that feels better. Run. Okay, come up to me afterwards if you want one. With that, are there any questions on the project or about side channel analysis in general?
Well, first of all, thank you. Come on.
Oh. I forgot, I have 2 blank PCBs too, so if you really like soldering. Yeah? Okay. Oh yeah, you really like soldering. You're not kidding.
Yeah, maybe we can use them as prizes for something. For somebody else. Yeah, I don't know. I want to have a built one.
Huh?
I want to have a built one.
Yeah, people don't like to solder.
No,
this is what I learned.
Too messy. How would you say that you would counter glitching problems when you're developing these things? What will you do as a developer to not worry about glitching problems?
It's very hard. The glitching problems, because it's really just that you can't necessarily trust the software to actually execute this stuff correctly. A lot of the glitching problems overlap with really high reliability software where they don't trust the hardware for other reasons, like it's running in space. So some of the solutions from that where they'll do the same operations a few times and then check the results can help. It's hard because if attacker is explicitly trying to screw up your hardware, it's not the same problem as random cosmic rays flipping a bit. Your attacker might be able to flip that same bit 3 times in a row. Offhand, it's not a very easy problem to solve. Most of it is considering what if I don't trust, every correct execution of every single instruction.
Right,
most of the time, if you can fix that,
They tried glitching like smart cards and stuff.
Yeah, so for the smart card, there's another, they have protection built into hardware. So they basically try to design into the hardware circuitry that it doesn't, it's more resistant to this. You can do stuff, on the chip to make it such that if the power drops out, it resets right away instead of
If you have,
partially running. Even that, people have gotten around, but it's more difficult.
Interesting. Do we have questions from now? I'm sure we have. No? Really? All right, in that case,